All right, welcome back to our journey through the explosion of mathematics. So let me ask you something. In a world jam-packed with these incredibly complex, powerful, and, let's be honest, sometimes fragile systems, what stops everything from just falling apart? I mean, we're talking about massive things, like our power grids or supersonic jets. Well, the answer isn't what you might think. It's actually a hidden mathematical framework that's quietly running our world. So, yeah, let's dive right in.
I mean, really think about it for a second. You've got a single power station that goes down. What's stopping that one failure from just cascading, into a total blackout across the entire continent? Or think about a massive bridge. It's getting hammered by wind, by thousands of cars every day. How does it stay so perfectly stable? And what about a jet flying faster than the speed of sound? How does it not just rip itself apart? These aren't just tricky questions. These are huge, super high-stakes problems.
And your first thought might be, well, just use stronger steel, right? More concrete. But the real solution, it turns out, is way more elegant than that. See, it's not just about building things to be brutally strong anymore. It's about building them to be smart. And that intelligence, that ability to actively control itself, well, that comes from a really fascinating branch of abstract mathematics.
Okay, so here's how we're going to break this down. First, we're going to really look at the problem of complexity itself. Then we'll get into the math that solves it, and you'll see how this one single theory works in totally different worlds. We'll even take a peek at where this is all headed, think microscopic, and finally, we'll kind of step back and just appreciate how powerful these abstract ideas can be.
All right, first up, the problem of complexity. Because before we can even talk about the solution, we've got to get our heads around the sheer scale of the challenge here. We're talking about these enormous, interconnected, and sometimes just plain chaotic systems that make up our modern world.
So for the longest time, engineering was basically trial and error. You'd build something, you'd push it till it broke, and then you'd learn from why it failed. It was all reactive, kind of a brute force method. But you can't exactly do that with a national power grid, right? Or a jet full of people. The mathematical approach just completely flips that script. Instead of waiting for things to go wrong, it's all about being proactive. You model the system to predict how it's going to behave, you optimize it, and you design stability right into its DNA from the very beginning.
And the tool that makes all this possible? This is the hero of our story, mathematical control theory. The best way to think about it is like a nervous system for our technology. It's constantly sensing what a system is doing, checking that against what we want it to be doing, and then making these tiny, super precise adjustments to keep everything perfectly on track. It is all about building in that smart, proactive stability right from the get-go, instead of just cleaning up a mess after the fact. Okay, so now for the really cool part. Let's look at how this one single abstract theory has this massive impact in completely different fields. Seriously, this is where it gets fascinating.
Okay, take a look at this. This simulation shows something pretty incredible. Up top, you see a nice, stable, supersonic flow of fluid. Smooth, right? But now look at the bottom. One tiny little disturbance, and boom, you get total chaos. Now, what control theory lets us do is basically run this in reverse. It can figure out the exact, tiny, precise little action needed. We're talking something as small as a puff of air to tame all of that immense energy and stop the turbulence before it even starts. It's amazing.
Let's bring this back to the power grid for a second, because it's a perfect example. You've got millions of parts, all connected. If one little thing fails, that failure can just rip through the whole network in seconds, and lights out for everyone. So how do you prevent that? Well, control theory lets us actually model the entire network as one giant mathematical object. We can find its weak spots and then design automated strategies that can react instantly to a failure, isolating the problem and keeping the rest of the grid humming along.
And this is what's so wild. Think about it. The problems are completely different, right? You've got supersonic air, you've got steel bridges, you've got electrical currents, but the math underneath it all, the principles of stability, of feedback, of optimization, it's exactly the same. It's one abstract theory, powering all these different worlds.
So if that's what control theory is doing today, what about tomorrow? Where is all this heading? Well, it turns out the future of control is getting smaller, like a lot smaller.
Okay, so right now, if you want to control the airflow over a plane's wing, you use big physical things like flaps and actuators. But the cutting-edge research, it's all moving to the microscopic scale. I want you to imagine covering a surface with thousands of tiny little micromechanisms. Each one can make these incredibly fine adjustments to a layer of fluid that's only millimeters thick. And by getting all those tiny local actions to work together, you could create a huge, large-scale effect using just a fraction of the energy. It's a total game changer.
And all of this kind of leads us to our final and maybe the most important question. We've seen what this theory can do,
But where does something this powerful, something that literally shapes our world, even come from? And the answer, well, it gets to the very heart of why we study mathematics in the first place.
There's this quote from Perrier, who wrote the article this is all based on, and it just says it all. He says, "This progress is also born from abstract research like the mathematical theory of control." Think about what that means. The solutions to our biggest, most practical, real-world problems, they didn't start in a lab or a wind tunnel. They started on a blackboard, with mathematicians just exploring these abstract ideas about how systems work.
So what this all really means is that there's this invisible mathematical nervous system running underneath everything. It's constantly sensing, predicting, and adjusting all the complex tech we rely on every single day. And that whole system, it's just incredible proof of how powerful a purely abstract idea can be when it comes to solving very, very real problems.
You know, this is only the fourth part of our series on the explosion of mathematics. We have so many more of these hidden mathematical worlds to uncover together. So if you want to keep pulling back the curtain with us, make sure you're following the Staiblocks channel.
And hey, before you go, let me leave you with a little puzzle for next time. Picture a sealed container, maybe like a plastic bottle. You can't change its volume without squishing it or tearing it, right? It's rigid. But what if I told you there's a geometric shape that can change its volume without tearing or stretching at all? Well, next time, we're diving into the totally weird and amazing Bellows Theorem. You are not going to want to miss it. Thanks for watching.